Hello, everybody. Today we're going to be discussing this amazing software called Intel Quartus Prime, or more accurately, Intel Quartus Prime Lite Edition Design Software version 20.1 for Windows. It is used for designing chips of all shapes and sizes, and of course, if Intel made it, it's going to be pretty based, pretty cool. The way the software works is that you have the user write some code meant for a hardware description language, or HDL. And then the compiler takes that and synthesizes that into an actual hardware design that could be printed out at a semiconductor fab or factory. The top HDL languages are Verilog and VHDL. And Verilog itself has a couple, like, you could say, sects or schools of thought in a way, because there's a system Verilog and behavior Verilog, but I'm not going to go into that. Languages like C, Java, Fortran, Python, etc. are not HDL languages, though there are C libraries apparently that let you make C behave like an HDL and translate that C code into HDL and then synthesize that into hardware. But that's kind of new stuff. It's kind of like breaking technology, breaking news type of technology, and it's not really the tradition. HDLs were traditionally their own thing. They're their own field, and I mean they don't even teach it. Like the average computer science dude or software engineering dude is not even going to write a single line of HDL code. They don't even know it exists. While your computer engineer or electrical engineer will know these types of things, because like I said, they're meant for designing chips. Anyways. Another thing of note is that the average user of such a program and programming language should have some background in digital design, or at least know some Boolean algebra that they probably learned from a class like discrete math. Why? Because this type of algebra translates to the gates you want to draw to design the circuit you want to make. All modern electronics, like microcontrollers, RAM, sound cards, CPUs, GPUs, and the like, are made of logic gates. However, if you don't know these things, that's fine, because one of the great things about Intel Quartus Prime is that it has a feature where you can just draw some diagram that you found online and convert that to Verilog and run it. And once you've confirmed that it works, like once you confirm that Quartus will compile it and that there's no coding errors at least, then you can take that code and run it through a simulator and test all the different inputs and outputs to make sure it matches with the truth table. The truth table, of course, has to be correct in order to be able to verify it. And yes, there are different ways of testing. The better way would not to be the better way would probably not needing to go and put it in a simulator, or like the more automated way would be just to use a bunch of test bench code. I don't have too much experience with like what the real guys do, but what we're going to do is like the absolute beginner stuff, where we don't even bother with writing test bench code and putting that test bench into the simulator. We are going to just manually change those inputs ourselves. Another thing is that we are going to be doing version 20.1, because that's the one that has model sim with it. There are the other versions, they do not have model sim. They pack some other simulation software, and in the classes I took, we ended up using model sim for the simulator. And you don't, like, hypothetically, you could go and download this version and download model sim separately. I don't like to overcomplicate. Just go and install 20.1. We're not going to do anything special that the new versions have. You go click this one. It downloads a tar file. And since this is a tar file, even though we're on Windows, that was kind of strange. That means that you're going to also have to make sure you have something like 7-zip installed, or WinRAR. WinRAR might be able to install it, but 7-zip's free. Go with that. Free and open source. And we got this here, right? Open that up. You see the setup.bat. I have this folder on my desktop, so I'm going to go like just drag that over here. and it takes a while. Even though I'm on an SSD, not an NVMe SSD on a SATA, but still. And then you would double click this, and that would be it. But uh, I'm not going to double click this because I already have Quartus Prime installed. I don't want to mess around and add another one. I'll delete these uh, for myself. Just go through the instructions, click on everything, install everything for the heck of it, really. Like if it says you want to install this, you want to install that, click out the check marks. Who cares? You should have plenty of hard drive space. Always have hard drive space. 512 gigabytes, that's not good enough. Go buy like several terabytes. Do not let them, don't never take less than a terabyte of space out of your computer as an answer. Always expand. All right. Joking aside, joking aside. So this is what it looks like when you have it installed. You got Quartus Prime Lite Edition, and for your very first project, let's go click a new project wizard. It's gonna give us introduction, whatever. You'll see this their default folder. Change that immediately. Do not save your project there. I repeat, do not save your project there. It freaks out because of permissions and that type of nonsense. Go and change this to something else. Go and change this. I got my desktop, my demonstrations folder. Put it here. We want to make a new folder. Call it something like this is going to be a full adder I'm going to make. So I'll just call this full adder. Select that folder and change that. Do not put it in the install directory. That default folder is the install directory. Don't let that happen. Gonna call this full adder as again, and we're gonna make an empty project. We don't have a template in mind. Now you see all this stuff. You see all this. Well, this isn't just a game. This is real. All of this is real. This code that you're gonna write, it's expecting you to write this Verilog code, and you have like some hardware target in mind where you transfer your Verilog code to a real device, a real FPGA. Because in the real world, I know this from one of my professors, when you're trying to test, so you got to go through a bunch of simulations, make sure all the simulations, all the timings are right, input outputs all right, logic's right, that type of stuff. And once all of that seems good, instead of sending it to the factory, then what you can do for an added layer of comfort and security to be sure that your Verilog code or VHDL code works out all right, you want to target an FPGA. You want to prototype on an FPGA. And prototyping on an FPGA is way cheaper than going and sending your code to the factory, getting it back, and seeing it doesn't do what you want it to do. So these are a bunch of FPGA models that Intel either supports or makes themselves. Intel does make FPGAs. They got a large division just for 8 FPGAs. You go there and click some random library family of products, and these are like all the models and stuff. And we always had some specific model in mind. We always chose Cyclone 4E, but any of these should work. I mean, you probably could choose like Cyclone 5, Cyclone 2. I don't even know what the real differences are besides the numbers here I see. And yeah, just choose something from here. Any of these can work. I'll choose, let's say, this one, because we're not doing anything complicated. We're doing a really small, simple project. And we couldn't mess with this. We can choose Model Sim here, Verilog HDL here. That's fine. True. But honestly, what we're gonna be doing, we don't have to launch Model Sim from here. We're not gonna do that. You can, but what I usually do is I write whatever I'm doing here, test it, and if I see I like what I see, And then I separately open model sim, and then I simulate from there. I open the project from model sim itself. So don't worry about the pathing. So let's make a new file. And instead of actually coding in Verilog or VHDL or System Verilog, this is another type of Verilog that gets its own category. We are going to make a block diagram file. Hit OK. And I got a design right here. This is what a full adder should look like. We have two XOR gates, two AND gates, one OR gate, and we have 3 inputs and 2 outputs. Correct? So we're going to draw this. We're going to convert it to Verilog code, and then we are going to test it. So let's see. Let's get some gates out. And over here, we have primitives. Everything we're going to be using is a primitive. Those gates I showed are primitive, all primitive gates. Another thing I'd like to point out is that even though I'm calling it primitive and what's his face, Quartus is calling it primitive, some professors like to tell you that XOR is not primitive enough just because you can make XOR gates with and OR gates. I do not care what they think, or is it and or not gates, something like that. I don't care what they think. If Intel is calling it primitive, then I'm calling XOR primitive. Okay? We're not here to argue. So, we want, and everything here is 2 inputs. So we got like OR 2s, or let's do XOR first. XOR. Gonna have those. Hit escape. Gonna hit the AND 2s. So we have like these different versions. They are like multiple inputs. AND 8 has 8 inputs. AND 6 inputs. You get it. Put some AND 2s. And then let's get OR 2. And that should be all the gates we need. Next, we want to actually have some inputs, and we will later connect these gates. So we have 3 inputs. We have an A, we have a B, and we also have a carry in. And for the outputs, type in out, or it's right here. We have here, and have this here. And let's go and name these. We're gonna call this A, B, and CN for the carry in. This is S for sum. What's that? Okay, good, yeah. And we have C out. Now, this design, by the way, the reason why we have things like carry in and carry out is the implication that you would later have multiple of these, like, kind of chained up, daisy chained or whatever, like a real adder. So this is a 1-bit full adder. This is a full adder. It's a 1-bit. You can add A, which is a binary number, and B, which is a binary number of both of them 1 bit. So A is either 0 or 1, B is either 0 or 1, and the C in, the carry in, is a 0 or 1. And then you could have, let's say, another full adder, and then this output would not connect to anything, but this carry out would connect to another full adder, and that would be like how you would carry the result. Like, let's say if you have A and B, both of them are 1, you would output 0. Over here, the output would be 0, and instead, you'd have an output at the carry out, and that would be a 1, and yet one would be carried to the next full adder. I guess I can show that too later on. But let's focus on just having this 1-bit full adder. So, time to connect these up. You just like drag, and if you can't get a straight line, you can drag upwards. And if you need, let's say, multiple connections, so over here, we see that we have these points. We want to draw more than one line. Oh, very well. We'll draw. Actually, it's not from here. Sorry. We'll deal with that later. Oh, actually, we do. We do have a point. So one of these inputs also go to the and 2 gate. Can even drag from the gate itself. And from this area, we drag towards this gate. All right, that seems like all the connections we need to make. Let's save this. You save it as a block diagram file. And let's run it. All this is really doing is going to just check that if there's any logic errors or whatever. Okay, cool. Something's missing a source. What do they mean by that? Oh yeah, we forgot something. We forgot to add the carry in. All right. See, that's good. That's good that we have this. We have the compiler. We don't immediately go to the. We don't immediately convert. We don't immediately try and simulate it. You should probably have more than 2 cores on your computer. Having a little more than that would be nice. I have 6 cores. It shows up as 12 over here because it's counting threads as processors, 12 of 12. So I have a Ryzen 5 3600. That's 6 cores, 12 threads. It's counting the threads as processors. Anyways, now that we've drawn our diagram, it is time to convert. So we're going to create an update. And yes, I think this is it. Create the HDL design file. And we choose Verilog VHDL full adder.v. That is correct. We hit OK. That was like instant right there. Relatively instant anyways. Right here. This full adder.v. We open that up. This is like Notepad or something. And we see here that Intel has wonderfully created this Verilog source file for us. We've got all the inputs, we've got all the outputs, we've got all the wires we need, and this is one module. And yeah, that's something I'd like to mention is that the more you do in Verilog, the more you design stuff in Verilog, the more complicated you get. Unfortunately, the less you'd probably want to design everything in one go. You want things to be a bit modular because things can get pretty complicated when you're trying to simulate stuff. You don't want to make something super duper complicated at once and then wonder why it's not working properly. If you make your device out of simpler components, then you can test those simpler components, make sure that in all those simple scenarios they work out. Then you take those simple components, make it into a bigger, more complicated component. So that's why, like with here, I forgot to make one of the last connections here. Let's say Quartus Prime didn't catch that issue. I went to the simulator and I was wondering what was wrong. Then I later looked up, found what was wrong. That was way easier than trying to wonder what would happen if I, let's say, did a 30 something, like 32-bit adder with, 32-bit adder at once, or even a whole arithmetic logic unit, try and do all that at once as one module. So, now that we have this, let's open up Model Sim. Okay. And it opened up on my other monitor, so pardon me. We're gonna make a new project. There was a window that appeared right here, but don't worry about that. Just hit close when you see it. We're gonna make a new project. Yes, close the current project if you have one open somehow. And I'm gonna go desktop demonstration. Wait, wrong one. Full adder. This one. Gonna call this once again full adder. Okay. And we're gonna add an existing file. Browse for that. This. Model Sim understands Verilog. It does not understand block diagrams. That's why you need to make the conversion. A lot of simulators, I'm pretty sure, are going to do the same thing. They understand this. They do not understand block diagram. Okay. Close. If you want, you can compile right here. Even though we already compiled it, we see, yes, compilation was successful. Now we go and simulate this. We want to test it out. Okay. So we got 3 inputs, 2 outputs. So to click on these, it even says in and out, and it says the values of these says high Z, state X, as in these haven't really been assigned anything. Drag them over here. And I'm going to I'm gonna whip out this website I found from Computer Vision and Biometrics Lab, I guess. Because that's where I found this link in and I was like, what is this for? Guess that's what it's for. Show you their whole page for it. Like, this is basically the same design. They got the logical expression. This is what the Boolean algebra looks like. But here we see the truth table. And they test out every single possible combination you could have for this. And they increment, go from, okay, change the carry in. If we have the A as 0, B is 0, carry in as 1, let's say, we get a sum of 1. If we have B as 1, carry in as a 0, sum of 1. If we have A as 1, B as 1, then carry in of 0, we get sum of 0, but we get a carry out of 1. If all 3 of them are 1, both the sum and carry out are going to be 1. So we have this as reference. We're going to test these values out, compare with the truth table, and see if they match up or not. So how do I do that? Okay. The reason I keep these names simple and I don't keep them super long is because I also have to type those out now. Force A, and I'm gonna put like, I don't know, I'm gonna put 0, force B1, and then force C in. I'll keep that as 0 right now. Then I'll run an arbitrary amount of time. We don't have to worry about timing or clock periods or clock cycles, anything like that. But in order for things to progress, you can't just have things happen instantaneously. So let's say I made this run 100. Okay. So we ran 100 and we saw that things are at state 1, B is 1, S is 1, state 1. So the sum is 1, we have no carryout. That's correct. We see here when V is 1 and the other two are 0, the sum is 1, carryout is 0. And let me force everything get to 0 right now. So I'm gonna just do force B 0. I don't have to change the others. Run 100. You see all of them are flat. Now, I don't know, let's make everything, all our inputs 1. Run 100. And boom, all of them went to 1. Let's test one other thing, I guess. Let's just test force C in 0, run 100. And we see that carry in is 0, sum is 0, but carry out is 1. Oh, by the way, if this is hard to see, you can always like zoom in and like change these a bit. Actually, zooming in, I guess, doesn't help that much. It makes it wider, but I've not really bothered with making the vertical, making it vertically bigger or wider. I don't know. All right. Well, I think that's that. I think I've taught what I wanted to teach. Except for one thing. Actually, well, one more thing. One more thing. One more thing. Perhaps I might cut the video right here. Let's see. So now let us, for example, I'm not going to touch that one. Instead, we are going to turn this. This would be an output, right? We want to turn this into a carry in, a separate carry in. And we're going to have 2 more inputs. This is a terrible way of doing it, by the way. This is not a very clean way of doing it. If I wanted to have 2-bit adder, I would have planned that from the beginning a bit better. I'll call this A2, call this B2. But yeah, first let's put the 2 XOR gates, the 2 AND gates. This is going to be the same, basically the same as the top one. We're using the same full adder design. Place that there. Place that there. And then for here, for this XOR, instead of having a carry in, we use the output from this OR2 and place it as one of the inputs for the XOR. And we're gonna have to also connect that to this. So let's bring these over. Oops. Come on. There. Let's stretch this over here, I guess. Now suppose this top one. Yeah, that seems legit. Seems legit. And the output from this XOR will go here. And we will connect these two inputs A2 and B2 to this AND gate. All right. Now we gotta add two output pins. Oh, really? I shouldn't have deleted that previous one, the previous carry out. I could have just reused that or kept it around, but whatever. We'll have one here and one here. And at the end of our XORs, that's our output. I'm gonna call this S2. So we have S1, S2, and this is gonna be our carry out. And now we have a 2-bit full adder, or more specifically, 2-bit ripple carry adder, where it's ripples over. Like you have to wait for this operation to be done, or like specifically like these three gates. You have to wait for these three gates to calculate, so you can get the output, so you can get the carry out, so you can do the calculations done over here. Oh shoot, forgot to connect this. So one thing that if you pursue this field of study is that you have to have realize that whatever you're designing, there's gonna be delays. Each of these gates have delays because in real life, let's say if you try to make such a circuit in real life, in real life, you'd be using transistors and you know the transistors when you're making the gates out of transistors, each of them is gonna have a delay. Each of those real gates are gonna have a delay. You're gonna be using like NMOS, CMOS, NMOS, PMOS transistors, NMOS transistors, and PMOS transistors. And when you make gates out of those, there's gonna be a like a nanosecond or picosecond delay, and you gotta wait for them for that for the signal for the voltage to pass through these gates in order for it to be over. Like as we were, if you were to make this like 64 bits entirely ripple carry, like I just keep copying and pasting this, then the delay to get your result is going to be much longer than just a 2-bit. So there's other methods of getting results faster. You have like carry look ahead adders. That's one of them. And those are a bit more complicated, and they have more gates involved. But yeah, this is the simplest. Ripple carry is the simplest type of adder. With 2 bits, we can also have twice the amount of information. Like so, we got like you know we have two outputs or three really, but 2-bit output. That means instead of just 0 or 1, now we can have 0, 1, 2, and 3. Wow. So this is great. And if you have like 8 of these, then you got an 8-bit adder, and you can have numbers up to 255. So you have an idea of if we were to expand this, we can actually start doing some real and useful math. But yeah, let's save this and let's convert it. Create HTML design. I'm gonna call this full adder. What the heck? Hey, No, what the heck? Hold on. Hold on. Yes, this one. Let me rename this. Call this full outer old, so we don't delete it. Okay. I should have also probably compiled this, but let's see. We had no warnings. Let's compile it. Five logic elements, 8 pins. That's a little more than before. Oh, by the way, don't worry about these warnings. 13, 14 warnings, that's normal for when we're doing things like this. Five logic elements, I suppose, it's talking about these inputs. And then the 8 pins, that's like we have 5 of these and 3 of these. Yeah. Alright. So we know it compiles. And let's open up models. And once again, it opens in the other window. So we're going to have a new project. Yes, that's fine. Now browse. Oh yeah, right. This is the right folder. Full adder 2. Okay. Add existing file. Alright. Gonna compile that. Alright, good. And you're gonna simulate and you're gonna see some results. See some interesting results. Hey. Is it loading still or something? There. Oh, I'm selecting these with the select and control by the control left click, control left click, control left click. Or you know, just drag them individually. And I'm gonna force A to be 1, force B to be 1, and force Cn to be 1. And we're not gonna. Oh, and we also have, even though we're not using this, like even though we want them to be 0, you do have to initialize them, even if you want them to be 0. Okay, so I want to make A, B, and Cn 1, and that should mean that we get an S2. S2 is gonna be 1, and S is gonna be 1. So let's go. Run 100. And wow, would you look at that? S2 is 1, S is 1, and our C out is 0. Now we're gonna go make A2 1 and A1. Wait, what the heck? B2 1. Run 100. Oh wow, everything is 1 now. We have 1 in state 1, 1 in state 2, and C out. And you know, we make A and B0. Alright, let me make a hold on. And then in this scenario, we can have with A as 0, B as 0, C in as 0, carry in as 0. Then we can have just a carry out of 1. State and state 2 are both 0. Okay, you get the idea. Thanks for watching if you made it this far. And have a great day. You should consider contemplate hitting the subscribe button, dropping a bomb on the subscribe button, obliterating the subscribe button, or firing artillery at it. Alright, see you guys later.